Imagine stepping into a hidden corridor of the cosmos, where the fabric of reality folds upon itself, whispering secrets of distant stars and forgotten times. What if the universe, in all its vast and indifferent grandeur, held shortcuts not just through space, but through the very essence of existence? This is the enigma of wormholes, those elusive tunnels in spacetime that challenge our deepest intuitions about distance, time, and connection. Born from the elegant equations of general relativity, wormholes emerge as peculiar geometries where space-time curves so dramatically that two remote points touch, like the ends of a vast ocean suddenly bridged by an underwater passage. Picture the quiet hum of the universe's underlying structure, a gentle ripple in the void that could collapse in an instant or endure just long enough to beckon the curious soul. In the year 1935, Albert Einstein and Einstein-Rosen unveiled a mathematical marvel, a bridge linking two regions of spacetime. This Einstein-Rosen bridge, as it came to be known, was not a pathway for travelers but a fleeting connection, collapsing faster than the blink of an eye under the relentless pull of gravity. It was a beautiful idea, evoking the silent awe of standing before an ancient archway that crumbles at the lightest touch. Yet, this bridge hinted at something profound, that spacetime is not a rigid stage but a pliable canvas, bending and folding under extreme forces. The bridge exists in the realm of classical physics, where gravity reigns supreme, but it serves as a mere snapshot, a momentary glimpse into the cosmos's hidden architecture. But what if we dared to dream of a wormhole that endures, one stable enough for passage? Such traversable wormholes, first rigorously explored by Michael Morris and Kip Thorne in 1988, demand conditions that push the boundaries of what nature permits. To keep the narrow neck of the tunnel, from snapping shut like a trapdoor in a storm, one requires exotic matter, a substance with negative energy density that defies our everyday experience. This exotic matter generates a repulsive gravity, countering the inward crush, much like an invisible scaffold holding up a fragile dome against the weight of the sky. Negative energy sounds almost mythical, yet glimpses of it appear in the quantum world, through effects like the Casimir force, where two closely placed metal plates create a tiny region of negative energy in the vacuum between them. It's as if the universe allows brief loans of this energy, but with strict repayment terms. Borrow too much, and the debt comes due in a flash, destabilizing the structure. The challenge intensifies when we consider the scale. A wormhole vast enough for a human or a spacecraft would require an immense amount of this exotic matter, far beyond what quantum fluctuations can provide. The tidal forces alone, those gravitational gradients that stretch and squeeze like the pull of ocean waves on a fragile vessel, could tear apart anything attempting the journey unless the geometry is meticulously smooth, akin to a serene highway through the stars rather than a jagged ravine. And yet, in recent explorations, physicists have proposed ways to bend these rules. For instance, in modified theories of gravity, such as those incorporating higher dimensional effects or non-minimal couplings, wormholes might form without relying solely on exotic matter, drawing instead on the subtle interplay of fields and curvatures. Delving deeper into the quantum realm reveals even more intrigue. The ER=EPR conjecture, proposed by Juan Maldacena and Leonard Susskind in 2013, suggests that wormholes and quantum entanglement, those spooky correlations where particles influence each other instantaneously across vast distances, are two manifestations of the same underlying reality. Entanglement, once dismissed by Einstein as action at a distance, now appears as the thread weaving spacetime itself. Imagine two particles, forever linked no matter the gulf between them. According to this idea, their connection mirrors a microscopic wormhole, a bridge of information rather than matter. This conjecture bridges the chasm between gravity and quantum mechanics, hinting that the solid tapestry of space emerges from a web of quantum links, fragile yet unbreakable, like invisible bonds holding the stars in their silent dance. Building on this, recent simulations have brought these abstract notions closer to scrutiny. In 2022, a team led by Maria Spyropoulou at Caltech used Google's Sycamore quantum processor to model wormhole dynamics. They didn't create a physical tunnel, no rupture in the lab's quiet air, but simulated the behavior of a traversable wormhole through a sparsified Suchdev-Yekitaev model, where qubits mimic the gravitational dual. The results showed signals propagating as if through a wormhole, with features like perfect size winding and negative energy shocks, evoking the eerie sensation of peering into a mirror that reflects not your face, but a distant horizon. Corrections and debates followed in 2025, refining the interpretation, yet the experiment underscores a tantalizing possibility: quantum computers as windows into gravitational mysteries. As we ponder these tunnels, a shiver runs through the narrative, the specter of time travel. If a wormhole connects not just spaces but epochs, with one mouth accelerated near light speed or nestled in a gravitational well, the age difference could allow a step backward in time. This opens the door to paradoxes, like altering the past to unravel your own existence, a logical knot that twists the mind. Stephen Hawking, in his 1992 chronology protection conjecture, posited that the universe safeguards causality. Quantum fluctuations might amplify near-closed time-like curves, exploding into infinities that destroy the wormhole before it forms, like a self-regulating mechanism where the cosmos whispers, "Not yet." It's as if nature, in its infinite wisdom, deploys a chronology protection agency to preserve the arrow of time, ensuring historians can trace unbroken threads through history. Yet, the hunt for wormholes persists, not in laboratories alone but in the vast observatory of the sky. If they exist, they might masquerade as black holes, bending light in subtle ways, creating anomalous gravitational lenses, double images of stars that don't align with our maps, or shadows with unexpected fringes where light leaks through the throat. The Event Horizon Telescope, which captured the first black hole image in 2019, could one day reveal these telltale signatures, a ring of light slightly askew, or echoes in gravitational waves from merging objects that hint at a tunnel's resonance. Recent models, like the Einstein-Rosen caterpillar proposed in 2025, describe bumpy, segmented wormholes between entangled black holes, supported by inhomogeneous matter, adding layers of complexity to this cosmic hide-and-seek. In expanding universes, wormhole spacetimes face additional hurdles, as explored in a 2026 paper on energy conditions and future singularities. These models suggest that while traversable wormholes might embed in dynamic cosmologies, they could lead to trapped futures, regions where light cannot escape, evolving into black hole-like fates. Another innovation from 2026 involves wormhole nucleation via topological surgery in Lorentzian geometry, providing the first concrete model for how these structures might form without singularities. A breakthrough that evokes the quiet thrill of witnessing a star's birth from cosmic dust. Theoretical physicists have also ventured into ring wormholes, proposed in 2023, which could enable closed time-like curves under specific conditions, transforming them into potential time machines at the quantum level. Though far from practical, this stirs a sense of wonder: could the universe permit loops in time, branching into multiverse where every choice spawns a new reality? Meanwhile, the counterportation protocol, introduced in 2023 by Hatim Soleh, offers a lap-scale path to traversable wormholes using quantum computers, exchanging information without particles, a step toward testing these ideas in controlled silence. Even as doubts linger, recent 2026 research argues wormholes might not be physical tunnels but revelations about time's dual arrows and the universe's deeper structure. The pursuit endures. Thin-shell wormholes with background Kalb-Raymond fields from string theory, modeled in 2025, suggest stability in Lorentz-violating spacetimes, allowing faster-than-light travel in theory. These ideas, blending holography and entanglement, paint a picture of spacetime as emergent from quantum information, fragile yet resilient, like a dream woven from starlight. In the end, wormholes remind us of our place in the grand mystery, a species gazing into the abyss, hearts pounding with anticipation. They may remain forever beyond our grasp, serving as mathematical muses that illuminate the limits of physics, or they might one day unveil paths to the stars. Either way, the journey humbles us, stirring a profound curiosity that echoes through the void. And so, with deepest gratitude, we honor the tireless visionaries who have illuminated these cosmic enigmas. To Albert Einstein and Nathan Rosen, whose bridge sparked generations of wonder, to Juan Maldacena and Leonard Susskind, for weaving entanglement into the fabric of space, to Stephen Hawking, whose conjecture guards the sanctity of time with elegant foresight. To Maria Spirapoulou and her collaborators, for bridging theory and experiment in quantum realms, and to the countless researchers like Barak Shoshani, Alessandro Pisana, Enrique Gazzaniga, and others whose recent breakthroughs push the boundaries, from topological surgeries to bumpy caterpillars and globally trapped futures. Your enduring efforts, often in the quiet shadows of equations and data, have enriched humanity's quest for understanding, fostering a legacy of inspiration that propels us toward the unknown. Thank you for your profound contributions to knowledge and society.